Quantum theory, also known as quantum mechanics, is a branch of physics that deals with the behavior and interactions of matter and energy at the smallest scales, such as atoms and subatomic particles. It was developed in the early 20th century as a response to problems in classical physics that could not be explained by the laws of motion and gravitation. The key principle of quantum mechanics is that particles do not have definite positions and speeds until they are observed or measured. Instead, they exist in a state of superposition, meaning they can be in multiple places or have multiple properties at the same time. This idea is represented mathematically by wave functions, which describe the probabilities of a particle's location and properties. Another important aspect of quantum theory is the concept of entanglement, where two or more particles can become correlated, so that the state of one particle is instantaneously influenced by the state of another, regardless of the distance between them. This has been confirmed through experiments and is considered one of the most bizarre predictions of quantum mechanics. Quantum theory also introduced the concept of quantization, where certain physical quantities, such as energy and angular momentum, can only take on certain discrete values. This is in contrast to classical physics, where these quantities can have any value. Quantum mechanics has been highly successful in explaining the behavior of atomic and subatomic particles, and has been confirmed through numerous experiments. It forms the basis of our understanding of the microscopic world and has led to many technological advances, such as the development of electronic devices and nuclear power. However, quantum mechanics is also a subject of ongoing research, as there are still many aspects of the theory that are not fully understood, such as the relationships between quantum mechanics and classical physics, and the interpretation of quantum mechanics itself. In addition to the above, it is important to note that quantum theory has a profound impact on our understanding of the nature of reality. In classical physics, objects have definite properties and exist independently of observation, but in quantum mechanics, the act of measurement itself affects the properties of particles. This led to the development of several interpretations of quantum mechanics, such as the Copenhagen interpretation, which states that particles do not have definite properties until they are measured, and the many worlds interpretation, which posits that every possible outcome of a quantum measurement occurs in a separate parallel universe. Another significant application of quantum mechanics is quantum computing, where quantum bits, qubits, are used instead of classical bits. Because qubits can exist in multiple states simultaneously, quantum computers have the potential to perform certain types of calculations much faster than classical computers. In addition to these, quantum mechanics also has practical applications in areas such as quantum cryptography, where quantum properties are used to secure communication, and quantum simulation, where quantum systems are modeled to study their behavior and potential applications. Overall, quantum theory continues to challenge our understanding of the world and has far-reaching implications for science, technology, and philosophy. Research in this field continues to push the boundaries of our knowledge and drive innovation in many areas. Another important aspect of quantum mechanics is the Heisenberg uncertainty principle, which states that the position and momentum of a particle cannot both be known precisely at the same time. The more precisely one property is known, the less precisely the other can be determined. Another key concept in quantum mechanics is the wave-particle duality, which states that particles can exhibit both wave-like and particle-like behavior depending on the experimental setup. This has been demonstrated through experiments such as the double-slit experiment, where electrons or photons passing through a barrier with two slits display both wave-like and particle-like behavior. Quantum mechanics also has important implications for our understanding of the structure of matter. The hydrogen atom, for example, can be explained using quantum mechanics, which shows that electrons occupy specific energy levels around the nucleus, rather than existing in a continuous cloud as previously thought. In addition to these, quantum mechanics has also been used to explain phenomena such as superconductivity, where electrons can flow through materials with zero resistance, and quantum field theory, which combines quantum mechanics and special relativity to describe the behavior of particles and fields in the universe. Overall, The study of quantum mechanics has revolutionized our understanding of the smallest building blocks of matter and energy and has far-reaching implications for a wide range of fields. It continues to be a subject of active research, as scientists seek to deepen their understanding of this fascinating and complex area of physics. Quantum mechanics is quantum mechanics and gravity. Despite its success in explaining the behavior of particles and energy at the smallest scales, quantum mechanics is not well suited to describe the behavior of gravity, which operates on much larger scales. This has led to the development of theories such as quantum field theory and string theory, which attempt to reconcile quantum mechanics with our understanding of gravity. Quantum mechanics has also had a profound impact on our understanding of the nature of time. In classical physics, time is seen as a universal and absolute concept, but in quantum mechanics, time is treated as a parameter, rather than a fundamental entity. This has led to debates about the nature of time and its role in the universe, and is an area of ongoing research. Another important area of study in quantum mechanics is quantum information and computation, which seeks to harness the properties of quantum systems to perform computations and store and process information in new ways. This has led to the development of quantum algorithms, which can solve certain problems much faster than classical algorithms, and has important applications in areas such as cryptography and optimization. In conclusion, quantum mechanics is a rich and fascinating area of physics that has far-reaching implications for a wide range of fields. Despite its many successes, there is still much that is not understood about the behavior of matter and energy at the quantum level, and research in this field continues to yield new insights and discoveries.